Good morning. Welcome. My name is Christian Karczynski, and I invite you to my entire course on limits. We start with lesson 1. It's a little introduction. We'll begin with the limits of sequences. But before we even get to boundaries as such, let's mention a few things. Firstly, it's very important to not be afraid of it. Limits are not that difficult. In the limit, it's really a calm topic to learn. So let's approach this confidently and optimistically. Everything will surely work out for us. Will you still generally have any difficult stuff with math in college? Maybe calculus, maybe more serious topics, but not limits. They don't belong, so you can completely relax and just learn. Today, we'll have a little introduction to sequence limits. Limits can generally be divided into sequence limits and the limits of functions. Today, we'll only talk about the limits of sequences and for a few more lessons. And we'll go through the most commonly used method of calculating limits, which will be extracting even from the highest power. Let's get to work. First of all, what do you need to know before even starting with the whole topic of limits? Not too much. Probably limits, if you have them, it's like the beginning of the semester, the start of the year, because you don't really need any knowledge from the university yet. Well, but still, like some basic high school algebra operations, unfortunately, you should revisit, maybe factoring out of brackets, and slowly I'll show what's needed. Powers, how they are abbreviated, operations on powers today, for example, will be very useful. Well, something like that, manage. General algebraic operations, as I wrote it technically. It's about getting familiar with these expressions. Adding x's, like when you add two negative numbers. What's the outcome? All that stuff. This collection of such completely basic stuff, unfortunately, you have to know to some extent, because otherwise you can't really start from scratch here. This journey with limits. First, let's talk about what the limit of a sequence even is. What we'll be calculating. I'll tell you, this won't be especially useful for calculations in practice. This theoretical knowledge, what a sequence limit is, and just take a look at it out of curiosity to get a rough idea of what you'll even be calculating. I emphasize once again, we're talking about sequence limits. The limits of functions will come later. Sequence limits are usually with the letter n, and function limits are usually with the letter x, so we will define ourselves, because here we will even attempt a formal definition of a sequence limit. To define the limit of a sequence, well, not a function. Alright, let's go. What is a sequence? An average example I think we remember. It's not any big magic. It's, for instance, continuous. An ordered series of numbers like 2, 5, 8, 11, 14, 17 and so on, endlessly. The next number in this sequence would be 20, right? This sequence is so nicely ordered. You can guess what the next number will be. In sequences, it's important to distinguish between something like a sequence term and the term's position. Look, here the term of the sequence is 14 and it is the fifth term. Because the fifth in order, that is the first. That is the second. That is the third. That is the fourth. That is the fifth. What's one thing is the term of the sequence, and what's another is its number in the queue. The sequence term 14, term number 5. Generally, we denote term numbers with a letter n, which usually means the term number of a sequence. So we have a sequence like 2, 5, 8, 11, 14, 17, and so on and so forth indefinitely. If we were to mark the terms of this sequence on an axis, we need it because we are heading towards the limit of the sequence. The terms of this sequence would be like 2, 5, 8, marked on the axis, right? 11, and so on, and so on, and so on. Here I started a new one. And so on, they could be drawn, 14, 17, and so on. Now let's imagine another sequence. 0, negative 2, negative 4, 0. Irregularity 0, negative 2, negative 4, 0. Then the square root of 2, the next term. Then some completely wild term. Nobody said that these terms have to be all nice. Let's just take some wild sequence here. This is also a sequence. If you were to mark his words on the axis, it would be 0, it would be minus 2, it would be minus 4, it would be the square root of 2, it would be... These terms would somehow jump chaotically along this axis. right? And there can be sequences like this too. And now let's imagine such a sequence. 1, 2, 2/3, 3/4, 4/5, 5/6, 6/7. These are the subsequent terms of the sequence, and so on. We see that there is some regularity in these sequence terms, and maybe we can say what it is right away. At the top, there's always a number that is one less than at the bottom. Look, this sequence described in this way could be described by what's called a general expression. This was all done on average. Such things, and in the general term, denotes the term number of the sequence. And see how it fits. If the term number of the sequence is the first time in the sequence, so we have a formula for this term, 1 times 1 times 1, which is 1 times 2, which is 1 times 2. If the position of a sequence term is 2, then we have 2 divided by 2 plus 1, which means 2 divided by 3, 2/3. So overall, generally speaking, etc., everything fits here, right? The whole sequence can be described by this single formula. And with this formula, you can, to say what, for example, will be its 100th term right away, and 100. It would be 100 over 101, 101, 100 over 101, 100, 101. That's how you would say it. Just as a side note, because all those sequences, you played with them in high school, I'm sure you remember. And we won't be bringing out all that high school junk, whatever that was. Oh my god. Monotonicity of sequences, arithmetic sequences, geometric sequences. Well, there was a whole big section on sequences, right? We'll focus specifically on the concept of a sequence limit. Look what I'm getting at. If we were to mark the terms of this sequence on the axis, just one after the other. Okay, just for orientation, I'm taking 0 for orientation because there's no 0 here, right? I just chose 0 to... So, catching on to A here. The first term of the sequence would be 1/2, somewhere here. Second to third, somewhere here. Then 3/4 somewhere here, a bit less, right? 4/5 next word, and sort of its subsequent words just like that. To highlight, 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 highlight on this axis here. Here, they would be less and less. Would drift apart less and less as if they were drifting apart. And the next ones as if to mark. Otherwise we wouldn't have such a situation as here. That 2, 5, 8, 11, 14, 17. And so we would grow evenly on this axis all the time. Neither here nor like here, jumping around on this axis completely chaotically without any rule. We only see our next marked words getting smaller and smaller. They would get closer and closer to a certain value, but never exceed it. And that value would be 1. Imagine if we took consecutive numbers. 7 eighths, then 99 hundredths. Million, million, and first. Closer and closer we would be to 1, as if we already had, say, 9 billion and 1 over 9 billion, we'd almost be around 1, but we would never actually reach it. And with each subsequent term of the sequence, we would get closer to that one, right? As if we were increasing it more and more and more. But we'd never actually reach 1. And then we say that the limit of this sequence here, or this one here, written in this way, is 1. If with each next word we approach something as if this sequence up here, the second one, the middle one, it doesn't have a limit at all. Because we're not approaching anything with each next word. And that sequence at the very top, you could say, it diverges to infinity. Because with each next word we go more, higher and higher and higher. We can say that it has an improper infinity limit. I'm a troublesome. I'm not giving it to you. Don't write all this down. Just calmly watch it to get some idea of what this sequence limit is after all. If we get closer and closer and even closer to this number, or when that's the case, it's the limit of the sequence. Let's try for a formal definition this time. Why not just take it easy? Just take it easy. It's not practically useful. Definition of a sequence limit, the formal one. Because what I just told you, Drew, well, that was all more or less. I use, for example, the term approaches. What does it mean you are approaching specifically? What's it about? It needs to be formally defined. Imagine that people all the time, for long hundreds, maybe even years, they used such a sequence boundary and calculated with it without formally defining it. Well, but we are already in the 21st century. We call the number g the limit of the sequence. That is, for example, 1 when, oh, and such a terrible thing, but slowly it doesn't come together. It's simple. Let's say this symbol means for everyone See, it's like an inverted capital letter A from English all, which means for all. Epsilon greater than 0. This is like a reverse D from the English exist. It signifies existence. It's for every and there is existence. So, for every a greater than 0, there exists such a number, n, such an indicator like n, that for every... So we already know the number of the term of the sequence greater than the one selected. What's the element of the sequence and him? Minus the limit is less than epsilon. What does that value mean? The absolute value of the term minus the limit? Perhaps we remember from algebra, or perhaps not. It represents the distance between the term and the limit. Look, the distance. Between the term, the continuous limit is less than some epsilon. What's this about? How to diffuse this limit? I'll phrase it a bit differently. For every epsilon, no matter how small an epsilon we choose, if I took epsilon as something like 1 billionth, 1000, no matter how tiny an epsilon I take, I will find such a term of the sequence, for example, starting from the 100,000th, starting from the 100 billionth, that the distance of a word in the sequence from this number upwards minus the limit will already be smaller than the selected epsilon at the beginning. A bit graphically, look, this is like the neighborhood of the limit of 1 and... If I take any small value as epsilon here next to this one, for example, for the gamma I'll take 100,000, so here almost it will be the vicinity of 1. I will still find such a sequence term number, like from the 100 billionth or from some. That from this number upwards, the terms of the sequence, starting with the 100 billionth first, 100 billion second, 100 billion third, will fall into this environment. They will fit here. So if I don't take a small epsilon, all the sequence terms from a certain point will still fit here in this vicinity. That's what the definition of a sequence limit tells us. You consider this a cool fact, because it's not going to be useful for practical calculation of limits. Alright, let's get going. Calculating limits, that's what we talked about. Now we're going to calculate it. And don't take it lightly anymore. Focus, let's get to it. So off we go. We have a sequence like this, and an equals n squared plus 1. It's kind of the recipe for its successive terms. Its first term would be 2. Why? Because if I take the term number 1, 1 squared plus 1 equals 2. Its second term would be 5, because the square of the second number is 4 plus 1, which is 5. Its third term would be 10. 3 squared is 9 plus 1 is 10, and so his next expressions would be formed, and so on and so on and so on. Of course, you don't have to describe it. To the second newest, lost. The fifth word is 26, the sixth word is 37. Right? Of course, this is yet another curiosity, and now we're supposed to calculate its limit, meaning what it's approaching. If we keep taking larger and larger n's, we need to examine it's written like this. Hold on a moment, just a sec. We need to examine what it approaches as we take larger and larger n. Does it converge to a specific number? Or does it get closer to 1? 5, so does it diverge to infinity, right? Look, this is how it's formally done in sequences. You take this sequence, you don't write an, but you take the sequence you're examining, its term, and add lim to it. Latin limes with n approaching infinity makes sense. As the sequence terms go towards infinity, they keep growing and growing and growing, and we need to investigate where this whole logical expression is leading. And now how is it done? Look, as you've surely noticed in class, if you've been bold enough so far, there are a lot of methods, etc. And we will be doing these methods too. But many sequence limits can be calculated without any methods. Look at this sequence. The n's are getting bigger, bigger and bigger. What could this be leading to? In the case of series limits, we will be strict, but we can neglect it a bit in sequences because it's not that essential. We'll often put various things on the side, such nonsense, and based on these symbols, we will be making assertions, determining where something is headed. Why such nonsense? Because look, infinity squared, what's that supposed to mean? What's this 8 doing here? This is not a number. It's just a symbol indicating that something is diverging, getting bigger and bigger, and we're squaring these results. And with such symbols you can figure things out, to catch on, to get many things by intuition alone, without any introduction formulas, without anything strict, because look, imagine it. You take bigger and bigger numbers, bigger and bigger, and square the results. Well, the results of this infinity squared will also diverge to infinity. As you increase the terms larger and larger, and each term is increased by 1, the whole will also become larger and larger and larger. So it will diverge to infinity. So this discovery, this is not a thing. The limit of this sequence is infinity, isn't it? Look at this sequence. You can see it goes into space. The numbers will be bigger and bigger and bigger. And look, I didn't give you any formula. Many such simple sequences can be solved without any formula, just by intuitively grasping the problem here. Substitute infinity for n somewhere on the side, and you look at what the whole thing is aiming for. Much can be done this way. Well, of course not all of them. It just so happens that 99% of cases, also in quizzes and exams, will be those, not all, where some methods have to be used. But at the beginning, it's good to go through a few simple examples like this, where you don't need to introduce any sequence limit methods at all, just like here. And now let's take another interesting case. Limits. You see, I didn't write this one at all. I didn't write this whole sequence, just straight to the limit from such a sequence. Generally in class, I suspect you'll have it this way. You won't write a, e, n and the limits underneath, but I'll just throw you the limit straight away. The limit as n approaches infinity of 1 over n plus 1. How is this done? Well, I substitute infinity for n on the side and I get something like this. And look, something diverges to infinity. It's getting bigger and bigger and bigger. And you increase these results by 1. I'm talking here at the bottom in the denominator. So we have 1 over infinity. Imagine what this could lead to. 1 over infinity. There's always a 1 on top in these fractions, because they turn out to be fractions, and increasingly larger numbers at the bottom. 1/2, 1/10, 100, 1 billionth, 1 trillionth. See, these numbers will become smaller and smaller and smaller and smaller and smaller, because 1,000th is smaller than 100th, and 100th is smaller than 1/2, and 1 billionth is already a very small number, and 1 trillionth is exceptionally tiny. So, the denominator keeps increasing, 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 and the number is getting smaller, smaller, smaller. What do you think this number is approaching? It probably equals 0. Yes. And here it is 0. This is how we come to the first such formula for the limit. Look, there are two, very important. Right away at the very beginning of the boundaries, write them down somewhere and remember them. First, the number divided by infinity, some fixed constant number in the numerator and infinity at the bottom. Everywhere it'll be this kind of situation. At the top there might be a number, say 10, 10 times 100 and 10 times 1000, 10 times 100 billion. It will always come down to 0. It's the first important formula to remember, and the second one. The second one, which isn't particularly useful for sequences, but is useful for function limits, is a constant divided by, not by 0, because there's no division by 0 in mathematics. It approaches either positive or negative infinity. We'll discuss this second formula more when it comes to function limits. Alright, I'll explain to you why it's not division by 0, but rather a symbol, and so on. Today we're focusing only on limits. Okay. Any other simple sequences, limits of simple sequences, the limit as n approaches infinity of n over 3 from such a sequence. So here at the top the numbers keep getting bigger and bigger, and we divide the results by 3, right? If you put that aside, just like that you're inserting infinity, aren't you? Because you would have infinity lasting for 3. How does that seem to you? It's also something you can understand entirely intuitively. Where is this headed? On the top, bigger numbers like 1, 3, 10, 3, 103, 1, 3, 1, 3, 1, 3. What does it approach? On and on, bigger and bigger. What will it converge to? It will diverge. The results will also be larger and larger and larger and larger, which means the whole thing diverges to infinity, equals infinity. If we marked successive terms of this sequence on the axis 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, so we would keep moving along this axis, flying all the time to the right without limits. Take such a sequence, it looks more intimidating, doesn't it? Oh, we're considering infinity here. And then here, slowly, when divided by infinity, we already know from the basic formula that it converges to 0. I'm talking about the first term. And here you need to think a bit. The square root of infinity, what would that be? Just imagine. The square root of a number getting bigger and bigger and bigger and bigger and bigger. they are also numbers that keep getting bigger and bigger. The square root of 100 billion will be more than the square root of 2 or 3, and so on. From those larger and larger roots will also be larger and larger. So as it grows, the square root of it will also keep increasing. So here we'll have infinity too. 1 divided by infinity, we know it's 0, so it also converges to 0. 0 minus 0 is 0. So this limit equals 0. Me too. So a simple case like that. We set infinity for... no. Look, infinity squared is still infinity because the number keeps getting bigger and bigger and bigger. And if we subtract 1 from those increasingly larger results, well, so these results will also diverge to infinity. So it'll be the same, right? 3. Through infinity, according to our 2 basic formulas, which one? I really would ask you to learn limits from the very beginning. Somehow I always say people should learn these 2 limits at the start of limits. No one ever does. So you do it, and a number divided by infinity is 0. So we have 3 minus 0, which means it converges exactly to 3. The result of this limit was 3. And just through such simple analysis and knowledge of this pattern, that a constant over infinity approaches 0, you can calculate many simple sequence limits. But how was it in those classes? It was calculated differently, wasn't it? Because in those classes, for example, it was like this. Look, let's consider something like this. The limit of a sequence, n over n minus 1. I am setting infinity here as a name, and it's cool. I don't have infinity. Is there infinity minus 1? Infinity minus 1. Well, it's still not there. I'm talking about the bottom, no problem. Because bigger and bigger, ever-increasing numbers were mixed up, and one also ran off into infinity. But what could this lead to? At the top, there's something growing bigger and bigger. And at the bottom, it's growing bigger too. Can we say that it somehow shortens and gives 1? No, because upstairs and downstairs it's not the same. Look at this fraction. You can't just reduce it as if there were 3 here and 3 there. This symbol here, this horizontal 8, doesn't represent any specific number. Divergence, so to speak. Here we have information that this diverges and that diverges. And nobody said we could reduce it like it was with numbers. So where is this heading? The hill keeps getting bigger and bigger and bigger. The valley keeps getting deeper and deeper and deeper. And crucially, here we reach the key issue, that we don't know where this is heading. To check where this is heading, we'll use various methods of calculating sequence limits. In such and a few other symbols. Let's get to work. I remind you, it was about such a sequence. After such initial substitution, we realize that here we have something like infinity divided by infinity. And we realize that we don't know what it's aiming for. Alright, let's formalize it somehow. This symbol and a few others, as I've mentioned, are so-called indeterminate symbols. And in these symbols, we won't know to what the sequence limit is heading. And in these symbols, we'll need to calculate some limit. And it turns out to be 99% of sequence limits, as I've said. You probably won't get something that simple at the colloquium or exam, like the one I calculated on the previous slide. What will those symbols be? Look, there are 7 of them. First of all, 0 divided by 0. These zeros here don't mean 0, but this is a symbol that something is approaching 0, no? Which is a symbol that something is infinitely small. Look, on top something infinitely small over something infinitely small. Where could this lead? It's uncertain. To everything. And to infinity, and to 5, and to 0. One must calculate, use some methods to see where it all leads. Something infinitely small by something infinitely small. I'll be calling it 0 by 0 for short, but that's just a mental shortcut, because there's no division by 0 here. Only dividing by an infinitely small number. In mathematics, there is no division by 0. Infinity divided by infinity. Here is our acquaintance from here. Minus infinity, look, infinitely. A large number, a reduced number. Something diverges to infinity minus something infinitely large. It's uncertain where this will lead. It's not necessarily to 0, no one said that. If those were 2 numbers, 10 minus 10, it would be 0, but those aren't numbers. There are some expressions that diverge into infinity, sequences that diverge. And subtracting their terms doesn't have to equal 0. 0 times infinity, which is infinitely small multiplied by infinitely large. Something approaches 0 and multiplies by something infinite. Something infinitely small and a lot of something infinitely big? Interesting, isn't it? It's also unclear what this is heading towards. It depends. It all depends on whether it accelerates faster or decelerates faster, in quotes, right? I'm heading to infinity. As you might guess, it's not about being exactly 1, because being exactly 1 would be what? 1 to infinity equals would be 1 chance, 1 chance, 1 chance. And where's the problem? That would result in 1, not always. But here's something. A bit close to 1, but not exactly 1, and diverges into infinity. We don't know where this is heading. Infinitely small to infinitely small and infinitely large to infinitely small. In short, I'll refer to it as 0 to 0 and infinity to 0. And in these 7 unspecified symbols, we must apply some different methods, which I ask you to somehow organize. That is, write clearly. When, however, separating one from the other. Not into chaos. But today we will get to know the first method, the most basic one, pulling out at once from the largest power. This method is used when we have a sequence in which there is a situation of a polynomial over a polynomial. Well, never mind, if you don't know what polynomials are anyway, don't worry about that. The boundary at an enormous infinity, and there must be something there, polynomial by polynomial. Look, here is a polynomial, n over the polynomial n minus 7. Polynomial by polynomial. That's the situation. Well, approximately like that. I wrote you that, because it doesn't necessarily have to be polynomials, actually. But alright. So, we go ahead like this. Look, pay close attention to these first 3 examples I will make. I will do it very slowly. Limits as n approaches infinity, n over n minus 1. The point is that at both the top and bottom, we rewrite the limits. Fac să copii the fraction bar. At the top and bottom, we extract the highest powers out of the brackets. When it comes to the mountain, there's only n there. So there's no point in taking out the common factor. If there's only one term, you don't take it out. I'm leaving n, and as for the bottom part, I'll play around a bit. The greatest power of n, where's the greatest power here? Only here. Right here, in n to the first, so to speak. Here's the greatest power of n in this simple example. So I pull her out in front of the bracket, that is n, parenthesis. What will it be? How is it done? Look carefully once. These 2 ingredients, this one, and then I need to divide by what I took out, namely by n. Let's start. The first n divided by n will be 1. I immediately wrote it down. I calculated it in my head, didn't write n over n. I wrote 1 right away. Minus, I copy. 1 divides by n, by what I extracted, and in this way such an expression is created. You understand? I extract the greatest power of n outside the bracket. Here what it is. I write this bracket and divide each of these ingredients by n. This one I did in my mind, and this one I didn't calculate. Well, because 1 through them, so what's there to calculate? 1 through them I wrote down, you understand. What did it give me? Look, n abbreviated with n, right? Up top, watch out, there's 1 right away. There's no 0 up top, so the fraction doesn't disappear, there's 1 on top, right? This is clear, I guess. And what next? Look, 1 over n, what does it approach? Remember, n approaches infinity, so here we actually have 1 over infinity. From 1 over infinity, from those 2 basic formulas. I showed you in the previous slide, it's 0. So I know this is heading towards 0. So I can replace it with 0. So what's left for us at this limit? Look, all the n's have disappeared, these are gone and that's gone. So I can already write the result. Notice, without the limit. Here I copied the limit, but here I didn't. There will be 1 at the top. And at the bottom, 1 minus 0, because it approaches 0. And 1 minus 0 is 1, so I write 1. 1 divided by 1 gives 1. Notice that I wrote limit here, but not here. Why? The principle is as long as n in the expression until... Alright. As long as there is an n in the expression, there's a limit, right? Of course. Once the n disappears, and here it has, you write without the limit. Don't rush. Take a close look at this. We'll do it very slowly in 2 examples. No, it can't be that hard. So you understand why this turned into 0. And that disappeared because here it remained 1. Multiplying anything by 1 is simply that thing, isn't it? Alright. Next example. We have something like this. This kind of action. Because it's a polynomial by a polynomial. Fractional line. I'm drawing out the highest powers of n. There's 1 component at the bottom. So I'll leave the bottom as is. But now I'm drawing out at the top. What do I pull out in front of the bracket at the top? The highest power of n. So here n, right? n. Parenthesis. The first component. That 3n. I divide it by what I've drawn out, which is by n. 3n. When I divide by n, I do it in my head. 3n divided by n. The n's cancel out, leaving 3. You could jot down on the side, on a piece of paper, this is 3n over n, n's cancel out, leaving 3. Do you get it? Minus, I copy the minus here, 2 divided by what I pulled out of the brackets, which is by n. 2 divided by n, it will be something like 2 over n. Do you understand where this came from? At the bottom there's only one ingredient for n, so I copy 4. What happens now? These n will cancel each other out, this one with that one. 2 over n approaches 0, because as n approaches infinity, here I have a constant over infinity. And over infinity it tends to 0. So what's left on top? The 3, because it's 3 minus 0, right? And at the bottom 4, so 3/4. And limit calculated. If I kept taking larger and larger in here, for an Abram it was 100,000 zlotys. 1,100 billion, I would be getting closer. With all this, I'd get closer and closer to 3/4. Factorizing. It's about making this cancel out, and these tails here converge to 0, and then you get the result. And let's take a longer example, I'll show you. That's how I say it. The highest power, the highest power. Because here's the dilemma, what to pull out on top, right? The highest power, which is n squared, I'm drawing out at the top, isn't it? eTrapez. Fraction bar. Look, we still need to extract at the top and bottom, because there are several terms at the bottom, right? But okay, for now at the top, n squared. The highest power at the top is n squared. We agree. Huge parentheses. And one by one, each of these components, this one, this and this, divide by n squared. First this one, n squared divided by n squared. I did it in my head. 1. Further, plus I'm copying plus here. Then I divide 2n by n squared. I write 2n over n squared. You can do it in your head, but I don't recommend it. Better to write it down. Minus, I rewrite 4 over n squared. Up there, I divided by n squared. Now I'm moving down. At the bottom, I'm taking out the prefix with the highest power of n, which is n squared. Parenthesis. The first term, that is n squared divided by n squared. N squared over n squared will be 1. Minus 1 over n squared will be here. Do you understand where that comes from? There's no such rule here that there must be a 1 at the beginning. That only came out from the calculations. This first term here I divided by what I pulled out, and I got 1. Look here, it didn't come out as 1. So it's not that simple. And now see, square meters cancel out, that's clear. But what about these 2n over square meters? Look, maybe we remember from high school. 2n over n squared, n cancels out and the square cancels out. And where the power is smaller, you cross it out entirely and subtract that power from the 2. So 2 minus 1 will be 1, so n remains. 2n over n squared gives 2 over n. I hope you understand why this was simplified. If not, calmly write it down somewhere on the side. For n squared you can write n times n. You have to understand here why this happened. This is middle school level. And why did I have to abbreviate? Because now I know that 2 over n is a constant over infinity as n approaches infinity, and I know this tends towards 0. This also tends to 0, and here is n squared. Someone might ask, okay, but infinity squared is still infinity, and 4 over infinity is 0, according to one of those two basic formulas I gave you, so it approaches 0. And the bottom also tends to 0, so what's left of all this? It has fallen, it tends to 0, which means 1 over 1, we have a result of 1 nil, and that's it. If you were to take larger and larger n, larger and larger n, larger and larger n, then the whole would tend towards 1. Is it difficult? No, it's not difficult. It's very simple. Let's go on. Good. I think that's the basic blueprint of how it's done. It's already okay here. Visible. Let's complicate things a bit. Let's take a board. We pull out even from the largest power. We know that at the top, we leave the top alone because there's only one component, and at the bottom, we pull out an n squared in front of us. Right? It will be so. At the bottom, because what n squared outside the parentheses? The parentheses. The first term by n squared. So what I extracted results in 1 plus, and this other one through the square will be something like this. Now look, n and s squared will cancel out, but not completely. It will completely fail here, but here only this square will fail. Truth is, when there was division of some x's or n's here. For the same base and different exponents, take the one with the smaller exponent, because here it's as if the first endo is implicit. So that one gets completely cancelled out. And here this number, well, we subtracted the exponents. 2 minus this one. And over n squared simplifies to just n. And here's the square. Not, you can write it down somewhere on the side. Why n over n squared is like that? Because n over n times n, right? And n gets cancelled, leaving 1 over n. So this n here, pay attention, it's important. This n here remains. It didn't get shortened entirely. And look, 1 divided by n squared tends to 0. And so we use the formula, a number over infinity, that's 0. What do we have left? 4 at the top and what at the bottom? So like n times 1 basically. N approaches infinity, meaning we are left with infinity at the bottom. Because it tends to infinity. That's infinity. So we have 4 over infinity. And 4 over infinity. One of these two basic patterns, this is 0. So it turned out that it approaches 0 because n remained at the bottom and diverges to infinity. So at the bottom there is infinity and at the top there is a number. A number over infinity equals 0. And yeah, you can get it that way too. Now let's take a longer one on top. Polynomial over polynomial. We pull out the highest powers, even the largest ones. Heads up. The highest power on top is n cubed. I'm leaving the bottom as is because there's only one denominator. See how much you have to share here. I despise each of these components, and there are as many as 4. I divide by what I extracted, which is n to the third power first, minus n to the third. By n to the third gives me minus 1. I wrote it down here. 2n squared divided by n to the third goes like this. Next, minus n over n to the third like this, minus 1. Dividing n to the third power like this. Now pay attention how this simplifies. Look, here n to the third divided by n to the fourth. How does it simplify? Here n squared divided by n to the third. How? Slowly. N to the third over n to the fourth. N to the third is a lower power than n to the fourth. So it simplifies completely. So here I subtract 3 from 4, I am left with 1. So it's as if the 4 was never there, right? All I have left is n at the bottom. N to the first can also be written, if that would make it easier for you. What about these fractions here? N squared over n to the third. N squared cancels out from n to the third, partially n squared in its entirety. And here remains only n, because 3 minus 2 is 1, n over n to the third also cancels out. N entirely, and we know 1 is left, right? 3 minus 1 equals 2, so n squared remains at the bottom. We have 1 over n squared, and here minus 1 over 1 to the third, and here nothing happens. So how will it be 2 divided by n equals 2 divided by infinity? Because I know that n approaches infinity. 2 over infinity tends towards 0. It tends to 0. It tends to 0. So on top, we've ended up with just minus 1. Because this to 0, this to 0, this to 0. At the bottom, I have n minus 1 over infinity. From the basic formula, the result is again 0. Right? It's not that hard. Maybe with this simplification, if you didn't catch on. Why here, for example, whole n to the third, and here it remained n? Go over it slowly once more. Don't move on until you understand it. Generally, once you get it, it's simple. It's just a number left. Minus 1 over infinity is also clear, because it tends towards infinity. Now something like this. Back to the classic, as if I'm pulling on top. At the bottom, the highest power, it results in something like this. On top, look, as if not in order now. First there is a number, then there is the square. Well, that's nothing. Each of these components, 2a and n squared. You divide by what you extracted. You'll end up with something like this. At the beginning, 2 over n squared will be 2 over n squared minus minus. And n squared over n squared gives 1s. At the bottom, it's classic, right? Then n squared gets shortened. That leaves us with 1. Here will be a square. It remains 1 over n and what? It tends to 0, it tends to 0, it tends to 0. These n squares cancel out entirely. What are we left with? Minus 1 and y. Because at the top we have minus 1. It tends to 0, I remind you, right? This is not there. So 0, minus 1, and at the bottom 1. Because this tends towards 0, that tends towards 0, it cancels out. So we have minus 1 over 1, which is minus 1 straight away. Result. And so, less conventional examples, look here. Limestat endozone goes on indefinitely. With this factorizing there are various tricks, and like here for example, you can do this task by multiplying everything at the top first, the two brackets, meaning this times that, and this times that, and this times that, and only then extract the highest power from the result. But it can be done more subtly, and that's what we'll do. Separately from this parenthesis we will extract the greatest power, and separately from this parenthesis we will extract the greatest power. From this bracket, when you extract the highest power, it will be n, because here the highest power in this bracket is n. That's why we pulled out a minus, and then over n gives 1, so like that. Then from this bracket we draw out n, which is the greatest power, and we are left with 4 over n minus 2, 4 divided by n as we know, and 2 divided by n equals 2. 2 divided by n over n gives 2. Here 2n divided by n gives 2. What did this give us? Look, n times n would be n squared, and it would cancel out with this n squared. Or you can do it differently. Understand n squared here will cancel out. Leaving just n that, n with this n, and it will cancel out to 0. What remains is minus 1, hence it's all fair game. Minus 1 times minus 2, that's plus 2. Divide by 1. At the bottom is 1, so it's 2 divided by 1, which is 2. And we have calculated it. Also by extracting like this before the parenthesis. You can also use this extraction method in situations like this. For example, when something is squared. What are we doing? So we don't bother with this square at all, we just copy it. Here in the middle, in this bracket, we draw out the greatest power from this expression and the greatest power from that expression. It will look like this. I hope you understand why this is 5 and why this is 4. And now what? This n with that n gets shortened. It approaches 0, 5/4 remains. And also that's squared, so it's 5/4 squared. We include this square in the final calculation, that is 25.16. So in the middle of what expressions? When you have a situation with a polynomial divided by a polynomial, you can also extract it in front of the parentheses. Now here we have a long one. So we extract the highest power at the top and the highest power at the bottoms. At the top it will be n to the 4th power. It happens to be, it's the greatest power. And at the bottom it will also be 1 to 4. It's also the greatest power. So we have something like this. By the way, this method is often called different names by lecturers. Some call it division. They actually do not just say divide the numerator and the denominator by the greatest power or by the power of the denominator. It doesn't matter. All roads lead to the goal. That's just my habit. Factoring out. So numerator isn't always in such a pure form. More on that in a moment. It has its own certain advantage. Well, look, when I pull out n to the 4th up there, it will be something like this. You can check it out slowly. And 1 minus 4 at the bottom will be something like this. 1 minus 4 cancels out all of these here. After reduction, for example, n squared by n to the 4th. Here's what n squared would be. To square it all down to 1 and n to the 4th power minus 2 would be n squared. So 1 over n squared would remain here. Well, all these would be zeros. So the result would be 4 over minus 8. That's what we'd have left. 4 over minus 8. 4 over minus 8 is minus 1/2. And that's the end of tasks. Now, such a boundary. We don't panic here because there is this element. In the middle, inside the element, we extract the highest powers outside the brackets. It will be something like this. They're getting shorter. The pennies are getting shorter. 4 through n goes to 0. 4 through n goes to 0. 2 by 2 gives, which means cube roots. I pull out the greatest power in the middle from this through that at the top, which means n squared. It would be something like this. Emma squared and Emma squared here get shortened. It tends to 0, it tends to 0. What remains is the cube root of 2/16, which means the cube root of 1/8. Notice that Limes doesn't write anymore because it disappeared. The cube root of 1/8 is 1/2. Because why? 1/2 to the 3rd power gives 1/8. 1/2 times 1/2 times 1/2, that is 1/8. And now, like a stronger thing with this extracting in front of the brackets. This is a good time for you to stop watching this presentation. Not everyone introduces such already more advanced things, like factoring out where everything is under some root, just like here, look. A lot of people stop extracting the prefix at this point, or maybe even earlier. So figure out how it looks for you in class. And if you had stronger applications of this method of factorizing, well, let's get started. This will also come in handy later. Look, lemma is a pleasant infinite ruler of something like extracting a common factor, as it is the root of corporeality. First, you need to extract the highest power under this square root. Right here inside under the square root. Do not touch the root. At the bottom you know what to do, but at the top. So it will be like this. At the bottom of the root I don't touch. Under the root I take out n squared in front of the parenthesis. So it will be n squared times something like this. Of course, there's no way we're taking any shortcuts here because these are subroots for now. Now, what do I have here? The root of 6 times this. Then I split it into 2 roots. The root of the first times the root of the second. And now the square root example. So how much will it be? So generally, the square root of x squared. More generally, not of n squared. That's not x. Although in this case it would actually be n, but generally it's not n. The square root of something squared is the absolute value of that something. The square root of x squared is the absolute value of x. And this absolute value can only take either a positive or a negative value. In our case, the square root of z squared will be the absolute value of z. The absolute value of n, if we know that n is a positive number, will be n, which means it will indeed be so. Was it really necessary to arrange that? And how do we know that n is a positive number? Well, n is first of all the number of the term of the sequence, well, that would be enough. But n tends towards infinity, which means it's positive as hell, one might say. So indeed, the absolute value of n will be n. Within the function, there may sometimes be a catch in some examples, because their x can approach negative infinity, for example. And then you'll have to write not x, but miti. We'll get back to this topic within the scope of functions. Just flagging the issue for you here, not going into detail. We'll talk more about it within the scope of functions. Because here the int will always be positive, and you most likely won't have any trouble with this. The first section to the square is simply 1 times the square root of this. I can't think of anything. Got some kind of combination here. That the square root of 1 plus the square root of this. No, you can't break down addition like that. And once we've gotten to this point, things become simple. N cancels out on top and at the bottom. This approaches 0, leaving us with the square root of 1 over 1, which is 1 over 1, that is 1. And we continue practicing. Remember, these examples are a bit more challenging. So see for yourself if you ever had it in your classes. For example, something like this. Something squared over something like this. At the bottom, you know what to do. You need to include the square before the parentheses. And at the top, you can use the multiplication formula and square it, subtly speaking. Inside here, in this bracket, see, this big bracket and this square do not touch. And in the middle, pull out n outside the bracket. And it would look like this. Here in the middle, after pulling out n at the bottom, it's clear what needs to be done, right? And now at the top, we have something times something squared. So we break down the first one squared here times the second one squared here. Right? A squared and m squared cancel each other out, so it approaches 0 here, everything. So what remains is 3 squared. That square doesn't disappear, right? So 9 over, and at the bottom we have 1. So the result is 9. Still such a limit, quite typical, but here will be something new, because when we factor out the highest powers, so you see these n's will cancel out a bit differently than before. This time there's a lower power of n at the bottom, so it will cancel out completely, leaving n. So it will be n times 1 at the top, which means n, and 1 at the bottom. So, since n approaches infinity, at the top there's infinity over 1. Infinity over 1. This is, of course, infinity. And infinity over any positive number is still infinity. That would be negative infinity. So, the result is infinity, and that can also happen. We understand why, right? At the top we have n, which means infinity, and at the bottom 1. Now something like this. So we're figuring things out here. Just like the example with the square root we had before, here is the cubic root. First we extract the highest power outside the parentheses, right here in the middle. So into the third, first we take out the common factor, it will be like this. Then we split it into 2 cube roots. That is the cube root times the cube root. And that's how it will be. The cube root of n cubed is just n. So these n and these n cancel out. At the top we're left with a cubic root of 1, which is 1, and at the bottom 2, so the result is 1/2. And such an example here, we'll be doing similar things in the next lesson on multiplication by conjugation, so you can focus here. How will it need to be factored out? Look, at the bottom again there's no problem, but at the top, do you think it will need to be done like this? First, under this root here in the middle, factor out the highest power and extract it beyond the root, and then pull out across the entire counter at once. Look, for now I'm not touching anything here, just pulling out an n squared in front of this root inside down. Later, and I'm splitting it into two square roots. The square root of n squared times the square root of this and the square root of n squared, as we've established, is the absolute value of n. So if n tends to infinity, then it will be n simply. So we have something like this. Do you understand how we got to this? I'll split it into two square roots. The square root of this times the square root of that. And the root for this square gave n. And now what do I do at the top? I'm taking out an e in front of the parenthesis. From this component and from this component, I'm taking out an n in front of the parenthesis. It will be like that. Look, 3n divided by n will be 3. And see, this whole ingredient, I treat all this as one ingredient. When you divide by n, which is what I pulled out, you're left with this square root. Look, all this, the whole term, this is an ingredient here, and this is an ingredient. How dividing this term by n leaves 3, and dividing the whole term by n results in something like this. We shouldn't get confused here and not do an over n, 2 over n, something like 1 over n squared by n again. Or something like that. You can write it down somewhere on the side. Copy it, make a big fraction bar, copy this component. A large fraction bar and divide by n, and you'll see n nicely cancels out, leaving the square root. So it'll be like this. No? Do you understand this transition from this to that? It's clear what's happening at the bottom. And they cancel each other out. We're home. It tends towards 0. It tends towards 0. And we have a somewhat odd result. But this is also a number. What remains is 3 minus the square root of 2 here. Because it tends towards 0. 4 plus 0. That is 4. 3 minus the square root of 2 over 4. That's the result. Now there will be some really weird examples. I mean difficult ones. Make sure now, really here, if you need this, but it's worth learning them because they are like quite instructive. For example, the square root of n plus 1 plus 3 over n, as n goes to infinity. What do? Calm down. As usual, we turn off the biggest power outside the parenthesis first and copy everything else, so it will be like this. Now, I split it into two square roots. The square root of n times the square root of that, except the square root of n now. So this component, it won't cancel out like in those previous examples, where it was the square root of n squared and it neatly gave the absolute value of n, which is n. Square root of n, maybe you remember from middle school, can be written as n to the half, and that's how I wrote it, as n to the half over the square root of this plus 3. Now what do? I can't just simplify this n to the half with this n because there is also this plus 3. In the entire numerator at the top, I cancel out the highest power outside the bracket, which is n to the power of 2, fractional power. It can be like that. Look, n to the half big bracket from this first term, again the whole. I am dividing by n to 1/2 and 2, which means dividing all of it by n to 1/2 and 2, so only this root remains. Here inside the root I do not divide by n to 1/2 and 2. It's 3 divided by n to the 1/2. So now this n to the 1/2, n is partially cancelled out. How? We completely eliminate the smaller power, and here it remains 1 minus 1/2, subtracting exponents 1 minus 1/2, so here it remains n to 1/2, right? It tends to 0. 1 over n and 3 over n to 1/2 also tends to 0. Because it is 3 over the square root of n, and the square root of something diverging to infinity, they are bigger and bigger barriers. Values, so it's to 0 to 0. It leaves the square root of 1 on top, and what at the bottom? Infinity. Because n to 1 and 2 tends towards infinity, so we have 1 over infinity, which results in 0 from the basic formulas. Look, here in 2 installments, as if we were extracting. First under the roots, well here there was one root. We had something like this. And then again the whole expression, the largest power before us, we had something like this. Pay attention from this step to that one step. Now we have a really strange example. Well, we're extracting under these roots. here it will be needed, here it will be needed, here it will be needed. So it will be like this. Now we split it into two roots, root of this, root of that. And here the same, square root of this and square root of this. Where did these numbers come from? N is 3/4. We remember from high school that n raised to the fourth root of n to the third was just n to the 3/4. There was a formula for that. The power of this expression went up to the numerator, and the degree of the root went to the denominator. That's why it was also n to the half, see? The power of n up, so 1k. The degree of the root, which is 2, means it's a square root. Degree down here, so the fourth root of n to the third is n to the 3/4. Times the fourth root of this, well, here I just rewrote it. Here I have 3 times n to the third, because it's the square root of n to the third power. Here, pay attention to, and I didn't mention earlier, 2n squared over 1 to 3, I'm not crossing this out or simplifying anymore. I'm assuming it will approach 0, I'm letting it be, right? At the bottom, coming back to this, the root of n times. So it will be the root of n, which is n to the half, will be something like this. And I extract the highest power on the top as a common factor. What power will that be? N to 3/4 or n to 3/2, the highest one. 3.2 is of course greater by 3.4, so I am turning the parentheses on at the top. N to the power of 3.2 will be like this, space. This whole expression is divided by n to the power of 3/2, and this whole expression by n to the power of 3/2. So in the second one, these n to the power of 3/2 simply cancel out in something like this. And here it will be something like this, right? Now how do we simplify these powers? Look, n to the power of 3.4 over n to the power of 3.2. How do you simplify the lesser one completely? So it leaves us with 3/2 minus 3/4, right? What does that make? 3/4. It's not actually that important. What is it? 1.5 minus 3.4 is minus 1.9. But it's important that something stayed with me, right? N to the power of 1/2, n to the power of 3/2. When this cancels out, it's completely gone. And here we subtract 1/2 from 3/2, so it will be n to the first. So basically, these 3/2 here will disappear. So at the top remains n, which is infinity. At the bottom, 1. This whole thing approaches 0, and this whole thing approaches 3. Because here we have 3/1, it goes to 0, that won't exist. 0, 3/1 will be 3. So we have infinity times 3, which makes infinity on top and 1 at the bottom. Thus, the whole result approaches infinity. Those were really such odd examples. But on their basis too, I mean, it's odd. They don't really go beyond our known pattern of drawing out, even from drawing out the greatest powers. And remember, the roots, you can also convert to powers. Like here I changed a 4th degree root to a 3rd degree power. And now we'll move on to later. And another example from the series of the strange. Strange. But at the same time, somehow lecturers like this kind of stuff. Look, no panic here. No panic at all. It looks very daunting when it's laid out like this. How should it be done? Of course, we're not going to raise it to 30. God forbid it wasn't so that 1 to 30 and n to 90. No. Imagine 1% to the 3rd power, 1% to the 3rd power, 1% to the 3rd power, and so on. 30 times. You'd have to multiply, right? Something like that. No. Newton's formulas would require some miracles. But let's see how it's done based on these previous examples. Inside the parentheses, we isolate the highest power, here the highest power, and here the highest power inside the parentheses. And leave those large powers alone for now. So it will be like this. Here, with 1 plus n to the power of 3, if I factor out n to the power of 3, it will be like this. With 4n minus 1, it will be so. So from this, attention to the signs, I'm turning off the prefix, which means here it will be minus 1 because there was a minus here. Plus 2 wheat. Now go upstairs. I have n to the 3rd times this and the whole to the 30th. So what's it going to be? N to the 3rd to the 30th times this bracket to the 30th, right? But similarly here, it's n times up to the 40th will be n to the 40th times to u to the 40th, n to the 50th times to u to the 50th. Yeah, sure, it's like we're in a little house. Look, n tot is n to the 40th shortens to n to the 90th, leaving us with 90 minus 40, or n to the 50th. And this n to the 50, with this n to 50, it cancels out nicely. It will be to 0, it will be to 0, it will be to 0. So the whole result will be 1 over 4 to the 40th. Because here it's 1 to 30th, which is 1. 4 to the 40th, 4 to the 40th. And here, note minus 1 to the 50th will unfortunately be plus 1. Because to an even number, it always gives plus. So we have this. Obviously 4 to the 40th, that would aid us in calculating this. Alright, the next sequence is unusual, but oh so simple. If we take out the highest power, which is n to the 3rd, it looks something like this. I simplified it to 0 because n2 and n3 cancel out. I won't write it out for you anymore. That 2 divided by n remains. All zeros, it's still zeros. Infinity times. 1 remains for us, and that takes us further. Give us infinity, end of story. You can do such one-liners to that one, what I gave you at the beginning that we pull in front of us. So when we have a situation of polynomial by polynomial, well, don't take it so absolutely rigid, no. Though you could also say it's numerator over numerator, and that in the denominator there's 1, but you know, here you need to add a bit of slack, and generally with sequence methods, they often intertwine. It's not that strict, that integrated, but I think it's sufficiently. However, there are some rules to easily navigate when to apply which method, especially since the examples in quizzes and exams are so characteristic. You get one example for such a method that is A, then B is for another, C is for another, right? And you can really catch on to all this calmly. Alright, now several examples on calculating sequence limits using the same method. Pulling out before the highest power but in exponential expressions. What does that mean? For example, like this. Is a number to some power n, right? I'll show you how it's done. But the principle is, it's harder, but the principle is the same. We just pull out the parenthesis to a higher power. Before you start factoring out, organizing all these powers is crucial so that it is the pure form number to n. How to do it? From formulas from high school. Look, 9 to the power of n minus 1 can be expressed as 9 to the power of n times 9 to the minus 1. And 3 to the power of 2n can be written as 3 squared to the nth power, but why? From high school, we recall these two formulas. You can jot them down. Something to the power of a number times something to the power of a number equals something to the power of the sum of those numbers. And I use that here, but as if I had, say, 9 to the power of n minus 1. And I jumped to the left. I jumped from right to left here. And I broke it down like 9 to the power of n and 9 to the power of negative 1, according to that formula. And all such leftovers like here, you will have something with n plus something plus number minus number. In this way, one must organize. And here at the bottom, I used the second formula, the one from high school, but in reversed. X to the a, and in parenthesis to the b is x to a times b. And here I had 3 to the 2n. If I took the right side of this formula and moved to this one, I wrote that it's 3 squared and then it goes into the nth power, right? So it aims to be a number to the n itself. So what did I do here? I just cleaned up. 3 squared is 9 and it's pretty nice. And it's organized the number to the n. And at the bottom also the number to the n. And you have to aim for that. And now we exclude the highest power from the bracket. So those 9 to the n. There's no doubt here about what's smaller and what's larger. Here there's just 9 to the 9th power and here is 9 to the 9th. It's turning off the prefix. It will be like this at the top. We know where from, right? Look, this whole ingredient when divided by 9. When dividing by 9 sec, it's not like dividing this by 9 sec separately and that by 9 sec separately. The whole thing divided by 9 duets, that is 9 duets. 9 duets gets simplified, becomes 9 to minus 1 and so on. Plus 1 over 9 to the nth, that's clear. It's probably clear at the bottom too. 9 to the nth with 9 to the nth cancels out. 1 divided by 9 yards, what do you think it leads to? 9 to infinity. 9 times 9 times 9 times 9 times 9 times 9 to infinity diverges to infinity, which means here we have 1 over infinity. So we use our basic formula that the whole transjumpiness tends to 0, meaning this tends to 0 and that tends to 0 too. For the same reason, so we have 9 to the minus first divided by 1, which is 9 to the minus first. And we remember from school that 9 to the minus first was 1/9. So, and if we don't remember, we left the results as 9 to the negative first. Or that would be good too, no problem. And that's how you deal with these power expressions. First, cleaning up those two formulas, then pulling out the common factor. Well, it's not over. It might get a bit harder. I'll show you different cases. Look at this. The cleaning stage here can be skipped because it's already tidy, it's sleek. Number to the nth times number to the nth, and here is number to the nth. So I immediately pull out the prefix from the highest power, and for now everything's very simple. But what now? Because 7 to the nth power divided by 9 to the nth power doesn't simplify here at all. Absolutely, you can't just fiddle around with it saying it shortens. And some 2 to n remains. No, that could be done in powers, not in exponentials. So, it's nothing like that. What do we do when we have a number and another number and they don't simplify at all? We split this fraction into such two fractions. And look, 7th to the nth over 9th to the nth is 7th ninths to the nth, right? N times this remainder here, which remains 7 ninths to the nth power times this remainder. And now 7 ninths to the nth, imagine what that will be. 7 ninths times 7 ninths times 7 ninths times 7 ninths equals infinity. Will it diverge into infinity like this 9 here? No, because 7 ninths times 7 ninths would already be a smaller number. It's times 7 ninths even smaller because it's a fraction. So it will be less and less, less and less, less and less, and unfortunately it will converge to 0, surprise. So the result is 0 because 0 times here leaves 1, which goes to 0, leaving 1, right? So it's 0. Now you see, here it turns out a bit differently. Here 9 to nth was heading towards infinity. Just 9 to nth I'm saying, not the whole expression to 0, and 9 to nth to infinity. And already 7 ninths to the power of nth is approaching 0. How can one describe this with a general formula, this thing you intuitively sense? If the constant to nth can be either infinity or 1, there is also a case, or 0. Infinity occurs when the constant is greater than 1. When we multiply numbers greater by 1 with each other infinitely, they keep getting bigger and bigger and bigger, essentially reaching infinity. If those numbers were exactly 1, not approaching 1, but exactly 1, to infinity 1, that's 1 times 1 times 1 times 1 times 1, 1, right? But if these numbers are fractions, the absolute value means that negative numbers are also possible. For example, negative 1/3 to infinity is also 0. Anyway, if these numbers are fractions, then it's a fraction approaching 0 as it heads towards infinity. We'll use this formula many times throughout the course. So it approaches 0, meaning the entire result is 0. Next, we have a slightly more complex example here with 3 exponential symbols divided by such. First, we clean up this 2 to the power of n plus 1, we convert to 2 to the power of n times 2 to the first. 3 to the power of n plus 2 is converted to 3 to the power of n times. 3 squared plus 4 to the power of n and 4 to the power of n minus 1 is converted to 4 to the power of n times 4 to the negative first. This is the cleaning up stage. Then we take out in front of the brackets the highest powers. At the bottom we don't extract because there's only one ingredient, but at the top we extract the highest power before us, which is 4 to the nth power. So it will be like this. In this first term I didn't simplify anything, just wrote it down like that. In the end there will be plus 1 because 4 wind instruments at 4 wind instruments give us 1. So what simplifies here? What do you think? 4 to the power of n and divided by 4 to the power of n simply cancel out. Add 2 to the power of n divided by 4 to the power of n. It's like 2 quarters to the power of n. And from this formula, 2 quarters to the power of n is fraction, yes. And yes, a fraction to infinity, meaning it will approach 0. And this will also approach 0. And so what remains on top is 1. So we have 1/4 to the negative first power, which can be neatly tidied up. 1 over 1/4 and 1 over 1/4 is 1 times 1. It is the inverse of 1/4, which is 1 times 4 first, which is 4. Now you might have also encountered factorials within sequences. Let's recall something about factorials actually from high school. For instance, something like n plus 2 factorial plus n plus 1 factorial. Oh, this exclamation point means factorial, just in case anyone was wondering. Don't panic, you'll see how simple it is. What is a factorial in the first place? A quick recap, for example, 5 factorial. It was something like 5 times 4 times 3 times 2 times 1, right? 7 factorial would accordingly be 7 tasks passing as 5, 4 shares 3 days 2x1. And generally any n factorial is like this, that number from which is strong counted, times a number 1 less, times a number 2 less, times a number 3 less, and finally times 1. When some people write it the other way around, there's also no problem. 1 times 2 times 3 times 4 up to that last number. And how much could that be? N plus 1 factorial, for instance. Because here we have such expressions, not surely n factorial plus 1 factorial, but what? The number from which the factorial is counted, that is n plus 1 times the number 1 less than it, that is n, right? Times a number 1 less than it, that is n minus 1 times a number 1 less than it, that is n minus 2 and so on times 1. You get it, right? And now there's no problem to spell out n plus 2 factorial or even n minus 1 factorial, right? And see, such an interesting dependency. You don't have to write out this n plus 1 factorial all the way to 1a. But look, it can be written like this. In proceeding, let's proceed. In wisdom, let's proceed. You understand? Because this expression from now on, from this n to 1, all this is n factorial, we have that formula above. So n plus 1 factorial means n plus 1 times already n factorial. And the point is to write all these expressions in this way, so that it's something times something times something, possibly times n factorial. Look, here we have such a limit. N plus 2 factorial, what will it be? N plus 2 times a number, 1 less than it, times n plus 1 and times n minus 1. And so on, it goes, meaning times. So, factorial of n plus 1 equals n plus 1 times factorial of n. Factorial of n plus 2 equals 100 times factorial of n. Don't try to memorize this. You need to understand it. And here n plus 1 factorial is n plus 1 times n factorial. So we have it this way. Factorial of n is taken out of the bracket. It goes like this. N factorial gets cancelled out, so we end up with something like this. Right here I've already multiplied the parentheses by themselves. Yes. And here I went out with a minus in the parentheses. It'll be n times n squared and so on. So it goes like this. After cleaning up, I have something like this. And here, a good extraction in front of the parenthesis will be something like this. I'll skip the cancellation here in this little fraction. I know it tends towards 0. 1 square plus 1 square cancels out, so we neatly get that result. So you break down these factorials, organize them, and then you take out the common factor. Also others already common, organize to the same. So there's also this task about factorial. It's such a strange expression. Newton's binomial, you might also remember it from high school. Newton's expression or whatever you call it. Anyway, when you have something and something in the brackets and there's no fraction line, so it was broken down from such a formula. Factorial of the top over factorial of the bottom times the top minus bottom factorial. So these entities here are actually strongly masked. So let's go. The factorial from the top divided by the factorial from the bottom times the factorial from the top times the expression from the top minus the expression from the bottom factorial. Just like that. I've already spelled it out strongly from above that this is n plus 2 times the number. 1 less than I times already n factorial. And here n and n cancel out nicely, leaving 2 factorial at the bottom. Here n factorial and that n factorial cancels out. 2n factorial and 2n factorial cancel out. And we end up with something like this. 2 factorial, I have already written it down. 2 factorial, what will that be? Just 2 times 1. So I take it, the fraction is layered. Something over something and over something. That is the main fraction line. So I have this divided by that. So I take this and multiply by the inverse of that, which means times 1 over n squared. So it turns out something like this. Here already at the top out of this bracket, and from this bracket I have excluded n before the bracket. N and n squared will cancel out. And I'll just go out for 1, maybe 2. Very simple, right? That's it with attention. So let's put it this way. Factoring out is not some hard task. But you need a lot of practice for this and start as in homework with very simple examples. I may have started with a few easy ones in the beginning and quickly moved to the difficult ones. Well, maybe not entirely. Maybe start with a lot of these simple ones where you have a classic polynomial divided by a classic polynomial. And when you extract the common factor even before the highest powers, that's when it's easiest to catch on. Do this slowly too. When you're practicing alone at home, don't try to shorten it. Try to understand everything. Why exactly something tends towards 0? Why did I do 2n over n squared there and immediately concluded that it approaches 0? Why? For what reason? Don't learn visually memorably without understanding that if there's a fraction it approaches 0 or something. If it's like this, I make a circle and write that it's 0 without knowing where it comes from and why at all. This is a very bad way to learn because you'll encounter a slightly different situation and mark it as approaching 0 when it actually won't be. So right from the start, within the limits, one tries to understand, not just by side pecking away when something heads towards 0. So yeah, Salma if you had problems here, got stuck, hung up on some basic high school patterns. I mentioned something about cancelling out and you didn't know why it cancels out. I strongly encourage you to review high school material. Check out the book, see how algebraic expressions were shortened. I'm talking about high school, but this applies to junior high too, while shortening these powers. Ask someone maybe. Always try to understand it. Set your mind to understand from the very beginning. Because if you learn by rote, well, it's not going to go well. It probably won't turn out well. That's it. Of course, homework is absolutely essential. If you don't do it, don't kid yourself that you know anything. only when you actually do your homework. Well, then you can move on to the next lesson. Remember that perhaps the university doesn't expect you to meet such a threshold as I did at the end and there on a certain slide. Sure, you had to extract under those radicals. Maybe it's a good idea to let it go and focus on what they require from you at university. And thanks so much. I also have a request at the end if you enjoyed this presentation. Did it help you at all? Or the whole course? And then the next lesson was useful too? And could you leave me a nice positive comment on Allegro or under my videos on YouTube? Or please, I also ask you to send me an email with your opinion on my course, which I will be able to publish on my website under your name and surnames. And that you agree to let me use this on my site there in the offers section. Thanks, that's it for now. I hope to see you in the next lesson and in the upcoming methods of calculating sequence limits. But we will move to function limits about halfway through the course.